Okay, today we're going to talk about chi-square test. More importantly, the chi-squared goodness of fit test. So what if we are interested in seeing if these crazy dice are considered fair? So what can I do to test for a fair die? Well, one thing we could do is a hypothesis test. And a chi-square test is one way that we could test for fair die. A chi-square test is used to test for the counts of categorical data. So far, all the other hypothesis tests we've been dealing with deal with numerical data. So now we're dealing with categorical, counts of categorical. And there are three types. There is the goodness of fit, which is for univariate. We have the test of independence, which is for bivariate, and the test of homogeneity, which is univariate with two samples. But we're going to focus on goodness of fit today. So what does our chi-square distribution look like? It is skewed right, okay, so most of the data is on the left. It's different degrees of freedom have different curves, so just like our t-curve changes with sample size, chi-square distribution changes based on degrees of freedom, which is based on categories. And as always, as your degrees of freedom increases, your curve shifts towards right and becomes more like a normal curve. Okay, so if my degrees of freedom is 3, meaning I have 4 categories I'm taking counts of, the chi-square curve might look as such. Again, if I'm increasing degrees of freedom to 5, it might look as such. And if I'm increasing degrees of freedom to 10, i.e. 11 categories, it might look like this. So chi-square assumptions, you need an SRS, reasonably random sample. You need to have counts of categorical data, and we need to expect each category to happen at least once. You cannot have 0 counts expected. Now it can happen in the actual observed, but not expected. And your sample size, you need at least 5 expected in each category. So combine those two together, we need at least 5 expected counts. So here's the formula for the chi-square variable. You have big epsilon, big summation, adding the observed value minus the expected, squared divided by expected. And we're doing that for every single observation, add it all together. I don't suggest doing this by hand. Luckily, the calculator does the work for us. So if you want a shorthand way of doing a chi-square test, utilizing the calculator, you can go to Statistics, Test, and chi-square goodness of fit. Now, in order to do this, you will be inputting in list and spreadsheets a column of expected values, a column of observed values. And I'll show you how to do that here in a minute. But just like all our other hypothesis tests, you will get output, and showing work utilizing the calculator means naming the test, chi-square GOF, goodness of fit, and writing each variable the calculator asked for, making your observed expected tables, and stating the chi-square value with the p-value with the alpha and your degrees of freedom. And degrees of freedom equals your number of categories minus 1. So chi-square goodness of fit test is used for univariate data. We want to see how well the observed counts fit what we expect the counts to be. So this is very similar to probability when we talked about theoretical versus experimental, okay? Theoretical is what you expect, is your expected count. And observed is just like your experimental, what you actually get when you perform the test. Use chi-square goodness of fit on the calculator to find p-values. And as I've already said, it's based on degrees of freedom, which is number of categories minus 1. So just like with all tests, we have a null and alternative. So here are the null and alternative for a chi-square goodness of fit. Our null will always be that the observed counts equals the expected counts of yada, yada, yada related to the problem. Your alternative will be the observed counts are not equal to the expected counts of yada, 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 whatever object you are talking about. So be sure to write in context. Relate to the object in question. Okay, so if you want to test a die that you have around the house, you can also find a virtual die if you can't find a die. And actually, this doesn't even have to be a 6-sided die. You could actually test more than a 6-sided die as long as you do more rolls. But if we're testing a 6-sided die with 60 rolls, again, we'd always start with our assumptions. Yes, we have simple random sample. Again, we don't know we have a loaded die. Our expected counts, if we're doing it 60 rolls, they have 6 numbers. 60 divided by 6 means my expected count is 10 for each number category. Again, if you are testing a die that has more than 6 sides, again, just make sure that your rolls divided by your sides needs to be at least 5. So if we're going to test a die, null would be the expected counts for each number on the die are equal to the observed counts. And your alternative are the expected counts for each number of the die are not equal to the observed counts. So you're going to set up a chart. So if we're using a normal die, has the numbers 1, 2, 3, 4, 5, and 6 with 60 rolls. Again, I've already calculated my expected to be my 60 rolls divided by how many numbers I have, 6. I'm expected 10 in each category. You're now going to actually conduct the test, roll your die, and provide the counts of what is observed. Okay, so you can have 0 in the observed, you just cannot have 0 in the expected. So if you want to see if you have a fair die, go on ahead, roll your die 60 times or more if you're testing a die with more sides, and using your calculator, list in spreadsheets, you can input your expected column and your observed column and run a menu statistics chi-square goodness of fit test to see, do you have a fair die? So let's look at a more practical example. Does your zodiac sign determine how successful you will be? Well, Fortune magazine collected the zodiac signs of 256 heads of the largest 400 companies. Is there sufficient evidence to claim that successful people are more likely to be born under some signs than others? Again, so we have 12 different signs here and the counts of how many people born under that sign were successful. So how many would you expect in each sign if there were no difference between them? Well, if we have 256 people, and we have 12 signs, we expect there to be equal to 56 divided by 12, which is 21.3 repeated. So again, expected can be decimal. Again, observed will never be a decimal, but expected keep decimal if it is a decimal. So expected in each of these, for each of these signs would be 21.33 CEOs here. So how many degrees of freedom do we have? Again, degrees of freedom for chi-square is categories minus 1. Well, how many categories, how many signs do we have? We have 12 signs. So 12 minus 1 is 11. So we have 11 degrees of freedom. So let's actually conduct a full hypothesis test here. As always, start with assumptions. We need a random sample. Again, it stated the word random, so random SRS check. We need to check that our expected counts are greater than 5. Again, we've already calculated what we're going to do with a chi-square test always is you need an expected column and an observed. So expected column we calculated from our total of 256 CEOs. We divide that by 12, so we get 21.3 in each one. Observed is what we actually got from the tables. So notice in the last slide, again, they told us based on their magazine collected data, they gave us the observed values. Okay, so what we're going to do now is we're going to put this into a calculator. So let's start with the null alternative. So the null is the number of CEOs born under each sign is the same. Our alternative would be that the number of CEOs born under each sign is different or not the same. Okay, so how we put this into the graphing calculator, again, we need a column of expected. We need a column of observed. So I normally label column number 1, label it expected or observed. So we have expected, or you can label it out. We have observed. And you type in the value. So we have 21.3. Okay, then you type in your observed. And again, I had 12 slides, I should end on 12. And again, always double check the numbers twice, just because the calculator can only calculate based on the numbers that you input. So double check those just to make sure that they are all correct. Okay, and from there, you're gonna go to menu, statistics, stat test, and notice your chi-square goodness of fit is right here. GOF, again, what is my observed list? My observed list, I like to label it OB or observed. Expected is EX. And degrees of freedom. Again, degrees of freedom is categories -1. We have 12 signs, -1 is 11. And enter. So notice here, again, if we're going to show the steps, again, this is the formula if you want to calculate by hand. Just be aware of where the formula is on the formula sheet, because sometimes multiple choice questions on the AP test might have numbers filled in into the formula, but you don't need to hand calculate by hand. Again, if you're showing work using the calculator, you're going to name the test, chi-square test GOF, must put GOF because we're going to talk about a different chi-square test a little later. And then put down the chi-square value, 5.1, put down the p-value, 0.9265. Alpha is not stated, so let's use 0.05. Make sure to write down degrees of freedom, DF equals 11. And just like all hypothesis tests, we then compare p to alpha. And here p is greater than alpha, so I fail to reject be true. There is not sufficient evidence to suggest that the CEOs born under each sign is different, or you could say is not the same. Okay, so same conclusion statement after you find your p-value and compare that with alpha. Okay, so let's look at another example here. We have a company says its premium mixture of nuts contains 10% Brazil, 20% cashews, 20% almonds, 10% hazelnuts, and 40% peanuts. You buy a large can and separate the nuts. Upon weighing them, you find there are 112 grams of Brazil nuts, 183 grams of cashews, 207 grams of almonds, 71 grams of hazelnuts, and 446 grams of peanuts. You wonder whether your mix is significantly different from what the company advertises. So why is the chi-square goodness of fit test not appropriate here? Now remember, the chi-square goodness of fit deals with counts. Do we have any counts of anything? We actually don't have counts here. Again, all those numbers are representing grams, okay? That is numerical data, okay? That is not a categorical count. So because we do not have counts of the type of nuts, okay, we actually have grams, that's numerical, we don't have categorical data. So what might you do instead of weighing the nuts in order to use chi-square? We could count the number of each type of nut and then perform a chi-square test, okay? So reminder, chi-square must be for categorical data, not numerical. So offspring of certain fruit flies may have yellow or ebony bodies and normal wings or short wings. Genetic theory predicts that these traits will appear in the ratio 9:3:1 based on the type of wings, yellow and normal, yellow and short, ebony and normal, and ebony and short. The researcher checks 100 such flies and finds the distribution of traits to be 59, 20, 11, and 10. So what are the expected counts and the degrees of freedom? Well, if we expect 9 out of 16 of the 100 flies to have yellow and normal, and again, how are we getting 16? We're actually adding 9 plus 3 plus 3 plus 1, that's a total of 16 proportions, right? Okay, so if we look at the first one, yellow and normal is 9, so that is my proportion of 9 out of the 16. So utilizing those ratios, our yellow and normal would have, again, we're coming from this first 9 out of a total of proportion of 16 will get us 56.25. Again, keep decimal for expected. Yellow and short would be the second one, 3 out of 16 proportionally, which would give us 18.75, again, out of 100. Ebony and normal, again, here would be our second 3 out of 16, 18.75. And lastly, ebony and short would be 1 out of 16, 6.25. So again, these are expected, keep decimal for expected. These listed here are your observed. But again, it's just asking expected, there it is. They are all at least 5, which is great. So we can do a chi-square goodness of fit. So degrees of freedom, how many categories do we have? We have 4 categories. And so 4 minus 1 would be 3 degrees of freedom. Okay, so are the results consistent with the theoretical distribution predicted by the genetic model? Well, that sentence is our clue to perform a full-on chi-square test. Okay, so we start with our assumptions. We have a random sample of fruit flies. Yes, it says the word random. All expected counts are greater than 5. We just created our expected column. And yes, they're all 5. You must state this, okay? Make sure to have a chart, expected and observed. So what you put in the calculator should be written down on your paper as you're showing work. You do not get full credit if you do not list out the expected values. So next, continue. Our assumptions have been met, so we need a null. Our null is the distribution of fruit flies is the same as the theoretical model. And our alternative is the distribution of fruit flies is not the same as the theoretical model. Okay, so you can calculate by hand, or I would utilize the calculator. So using the calculator, go to your list in spreadsheets. Again, column 1, you're going to list the expected values. Column 2, you're going to list observed. Make sure to actually title the 2 columns. So showing work for calculator, name the test, chi-square goodness of fit. Again, from the calculator output, you should get a degrees of freedom of 3, a p-value of 0.129, and since not stated otherwise, alpha will be 0.05. Also make sure to state the chi-square value from the calculator output, 5.671. Okay, and based on our p-value, compare p to alpha. Since p is greater than alpha, I fail to reject the null. There is not sufficient evidence to suggest that the distribution of fruit flies is not the same as the theoretical model. Okay, so make sure that you have all steps, assumptions, null, alternative, either hand calculate chi-square or name the test, write down all the output from the calculator, make sure you have an expected and observed count, and a final conclusion statement. That concludes chi-squared goodness of fit.